Hello and welcome to problem 21 in my Calculus 3 or multivariable calculus problem solving series. In this video, we're going to look at how to evaluate line integrals. In Calculus 1 and 2, we looked at integrals in 2 dimensions. And we learned that the integral is a sum of all these little tiny pieces below the curve, and you add them all up to get the area from point A to B under the curve. But now in multivariable calculus, we're going to look at integrals in 3 dimensions, or line integrals. These are integrals along a curve in 3 dimensions, which pretty much do the same thing, which get the area underneath the curve. So if this was like a curtain on a stage, which was curved around like this, and the curtain had a length of f, the function, then the area would be this integral here. So in this video, we're going to show you how to calculate these integrals. And so if we want to integrate along the curve C, which runs along the xy plane, we need to parameterize the curve C. To do this, we're going to define a function r in terms of t, which will be the curve C. And it will be parameterized by t with 2 functions, g and h. So now that we have r, we can use it to find this integral. So the first thing we're going to do is we're going to set t to be from A to B. So those are going to be the bounds on t. So A is less than or equal to t, which is less than or equal to b. The next thing we need to do is to find ds. Now, in this integral, ds is going to be a small piece of the curve. So what this integral is doing is taking the small pieces of the curve and multiplying it by f, the length. So to find ds, we're going to use r. And you can think of ds as a small arc length of the curve. So to find the arc length, we need to take r prime. So ds is going to be equal to the magnitude of r prime of t dt. And so this is what we're going to use in the integral. So finally, when you substitute everything, you get this integral. So you transform this integral into this, where you have an integral from a to b of f of gt comma ht times the magnitude of r prime of t dt. And the reason you have this, the parameters of f in this form, is to have everything in terms of t. So the variable that you're integrating in this integral is going to be t. And so this will give you the line integral, or the area underneath the curve. So another property of line integrals is that if you have a piecewise function, meaning that it's divided into multiple functions, different functions along different intervals, then you can represent the line integral of the entire function as the addition of different line integrals for each of the functions separately. So for example, here we have a curve C that's continuous and is represented by 3 different functions, c1, c2, and c3. So you can represent the line integral for the entire curve as the line integral for c1, the line integral for c2, and the line integral for c3 added all together. And this works for however many functions you have, as long as they are all continuous. So let's go ahead and look at a problem using line integrals. So this question says, evaluate the line integral where c is the right half of a circle with radius 4, traced out in a counterclockwise direction. So I've drawn a picture here on the xy plane of what C looks like. So the curve will go from the point 0, -4, and it will go to 0, 4 in this direction like this. So it follows a counterclockwise direction. And f is going to be the function x times y to the power of 4. So our integral is going to be f times ds. So first we have to find r. And r is going to be the function which represents c. So r is going to be 4 times cosine of t, comma 4 times sine of t. And this function will represent the curve c on all these points for when t is between -π/2 and π/2. So those are the bounds on t which limit it to these points. Next, we need to find the magnitude of r prime. So r prime, we just have to take the derivative of each one of these components. So the derivative of 4 cosine of t is -4 sine of t. The derivative of 4 sine of t is 4 cosine of t. And when we take the magnitude, remember we're taking the square root of its components squared. So we got 16 sine squared of t plus 16 cosine squared of t. And using trigonometric properties and identities, we can combine the sine and cosine to make 1. And we find that the magnitude of r prime is 4. So then we can transform this integral into this, where it says the integral from -π/2 to π/2 of 4 cosine of t times 4 sine of t to the power of 4 times 4 dt. And then when we solve the integral, we have to use u substitution, and we get this number here, 8,195 divided by 5. So that'll be the solution to this line integral and this problem right here. So hopefully this video helped you understand how to compute line integrals and how they work. If you like this video, make sure to like and subscribe and leave a comment down below what video I should do next. Thanks for watching.